Welcome to Operating Systems lecture 34. So we are discussing file systems, and we saw that one file system operation typically involves multiple disk writes, right. So examples being create of a file, you need to write to the parent directory, you need to write to the inode, you need to write to the data blocks, right. Similarly, append to a file, you need to write to the data blocks, you need to write to the index, you need to write to the inode. Truncate, same thing, but this time you are removing blocks from the file. Appending was adding files to the blocks to the file. Truncate is just removing files blocks from the file. So let's say you truncate just removes the last few blocks from the file, and unlink, similar thing, you're just removing a file from a directory. And once again, all these operations involve multiple disk writes, typically 4 to 8 disk writes per operation. And the problem we were looking at last time was what happens if there is a power failure in the middle of one operation, right. And so the problem is that it leaves the disk in an inconsistent state, and that can result in many bad things to happen. So two, and you can sort of categorize them into two types. One is dangling pointers, where you have a directory pointing to a file which didn't get committed to disk, which didn't get written to disk, and so the directory is pointing to some free disk block, right. So that's a possibility, and that's a very dangerous thing. Firstly, because when power comes back on, there's no way to figure out whether this is a dangling pointer or whether this is a real pointer, right. So if that dangling pointer is actually pointing to some block that looks like an inode, suddenly the user will have access to this particular file that it was not supposed to have access to, right. Any logic that depended on the contents of that file for the user's program is going to cause crashes. More, what's worse that can happen is the user can gain access into somebody else's file, right. So dangling pointers are a very bad thing, and you would ideally want to avoid dangling pointers. The other problem that can happen is disk block leaks, right. Here what can happen is that you basically initialize some data, and you are about to create a pointer to this data from the index. Let's say you were appending to a file and you created some blocks at the end, and now you wanted to change the index in the inode and point to those blocks, and there was a power failure in the middle. So what's happened is you have initialized some blocks, you have removed those blocks from the free list, but you haven't really created pointers to them before the power failure happened, right. And so when the power comes back again, what you're going to find out is that there are some blocks that are neither present in the free list and nor are they part of your directory tree or your file tree, right. And so that's a bad thing also, because there are these disk blocks that will never be used, and if you keep doing this, if you just keep having power failures, unannounced power failures, then eventually you can have lots of leaks, lots of space in the disk that can remain unused forever, okay. But in any case, disk block leaks are less dangerous than dangling pointers. It's not a correctness problem, it's a performance problem, right. So the solution we were looking at last time was, let the file system order the writes in a way such that it avoids dangling pointers. So we say, one of these has to happen. After all, there are multiple disk writes that are happening, and I cannot make them atomic with respect to power failures. Power can go get out at any time. So I have a choice between dangling pointers and disk block leaks, and I'll choose disk block leaks over dangling pointers, okay. And so basically the idea is that I'll order the writes to the disk such as I'll avoid the dangling pointers, and which basically means that when you're adding something, for example, I'm creating a file, I will first create the file, or I'll first initialize the data blocks and then create a pointer into the index, right. So this way there will never be a dangling pointer, because the index pointer will only be created after the data block has been initialized. In general, whenever there's a data structure like this where block A is pointing to block B, then you will first do this and then do this. Well, I am talking about create. So you will first create the block B and then add an entry for it in the index A. So you will first do this and then do this for create. On the other hand, when you are doing unlink or truncate, when you are removing things, you first want to remove it from the index and then deallocate or free or uninitialize these blocks, right. So if I am doing unlink or truncate and I have a structure like this, if I deallocate this first, then I have a dangling pointer. So it's better to first write to A to remove that pointer and then deallocate B, right. So you will first do A and then B in this case, right. So first I have written it in the other way actually. So yeah, this is a mistake. So first child or data and then parent or index, and first parent and then child or data, right. So that's okay. All right. Okay, so that's actually but in all this discussion I am assuming that all operations have to happen synchronously, which means I'm assuming a write through behavior, right. I'm saying that if I make an operation it should go to the disk, because after all immediately, because if I'm writing my code I'm saying update the index then update the file, then and I want it to happen synchronously, because if it's not happening synchronously and if I'm using a write back cache, then even though I did these operations in a certain order, what will really matter is in which order were these data blocks flushed to the disk, right. So it can happen that in the cache I did this first and this later, but when it was actually flushed to disk this happened before this, right. So all there is no use for ordering if there is a cache. Okay. So in general doing sync writes is not very performant, but it has this nice safety property that you can order things to avoid dangling pointers, and this was indeed used for some years in many operating systems in the early days, right. But we know that this has a very big performance penalty. But let's also look at another thing. Is it always possible to do this ordering? So let's say I had an operation that said move a file foo from directory A to directory B, right. So let's say I wanted to do this, and so this is, let's say, the rename operation, and I wanted this to be atomic with respect to power failures, or I wanted to make sure that things are safe, right. So in this case there are two things that need to happen. Let's say this is A and this is B, these are directories. Earlier A was pointing to foo, and now you want to remove the pointer from foo and create a pointer to foo from here, B from, right. So now in this case you may want you may want to say what should be done first. Should I remove this pointer first and then create this pointer, or should I first create this pointer and then remove this pointer, right. So there are two options here. I can either do this first and this second, or I can do this first and this second. In both cases my file system on a reboot can appear in a very inconsistent state. So it's no longer the case that one of them will only result in a leak. If I do this first, so let's say I do this first and a power failure happens before I had deleted the second pointer, I have a situation where one file is being pointed to by multiple directories, right, and this may not be acceptable, and there is no way an operating system, so depending on the file system semantics this may or may not be acceptable. So let's assume that it's not acceptable, and there's no way that the file system can automatically figure out what to do, right. So when it comes back again and it figures out there's something wrong here, it will probably want to say I either want to remove this or I want to remove this, but has no way to figure out which one to remove. So at that point there are a couple of options. Either you ask the user, look, I see some inconsistency, a file seems to be part of two directories, or a data block seems to be part of two files, it's similar, then what do you want to do? Okay. So those are options, and these are things that you may have seen in programs like fscheck, right. So there are these programs that run on, if you have not mounted your disk cleanly, then when you bring it back again, there's a program that will do a global file system traversal and figure out if there are any inconsistencies. And the advantage that ordering gives you is that you have limited the inconsistencies to only certain types. In this case, perhaps it makes more sense to do this first before that, right? Because at least you are not losing data. You have some inconsistency in your state, but at least you are not losing data. If you had deleted first and then created, then you would have lost some data, right? So you have to basically you have to do some ordering, and depending on what ordering you're doing, you have guaranteed that you have limited the types of inconsistencies that can happen on a power failure. And then you have a program that will be a long running program that will probably do a full file system traversal to figure out the inconsistencies and either fix them itself or ask the user to fix them first. Yeah, question.
So like in case this first and second both of these things were drawn up, and after that there was a power failure. After that, when the disk reboots, how does it differentiate between whether or not the previous command was a move or whether it was something in the form of a shortcut creation?
Right. So let's say I'm using this strategy where I'm going to first create and then remove, right? And before I did a remove, there was a power failure, right? So let's say there was a crash at this point, and so I have a file system state which has one file being pointed to by multiple directories. Now the question is, how do I differentiate? How do I know what is going on? Actually, I have no idea, right? So there's no way to figure out what was going on at that time. All you are going to do is try to bring it in a consistent state in some way.
So no, what I'm saying is it might be possible that this was a consistent state, that there are two pointers to that. Like,
well, yeah, I mean, so your file system may your file system may allow this kind of a thing, and this may look like a consistent state. In which case, the file system may actually not throw any warning at all, and it's for the user to actually now deal with things on his own, right? But assuming that the file system does not allow this kind of a thing, and this is actually an inconsistency in the file system for semantics, then it can throw a warning to the user. All right, okay. So basically the idea that I've discussed so far is that you're going to order the writes on the disk in a certain way to limit the types of inconsistency that can happen, and then you're going to run a program in case of an ungraceful shutdown. So when you come back again, this program is going to do a global scan, and it's going to figure out what inconsistencies there are and trying to resolve it either automatically or using users here. Right. So this has actually been used for a long time in lots of different operating systems, and perhaps you have seen this also in the regular operating systems. But this has a few problems. Firstly, as the disk size becomes really large, the time it takes to run this fscheck program, which is a global scan of the structure, becomes really large, right? So just to give you an example, a random read. Yes, question.
Sir, but earlier we have said that we kept 2 copies of the table, file table.
Okay.
Like file allocation table, we said that. So can't we use that to figure out what is the inconsistency?
All right. So the question is that we have also said that for reliability, we will duplicate state. Some state we will duplicate. In the case of a file allocation table, I will keep 2 tables, right? And so can that help in a resolution of such conflicts? See, when we duplicate state, we are basically doing it for reliability against stationary disk errors, errors that can happen over years and things like that. And you don't want duplicate state, you won't design a file system such that duplicate state basically involves updating twice for every update. So you won't design your file system typically to say that every time I make an update, I'll have 2 copies of every inode, and every time I make an inode an update to the file, I'm going to write twice to 2 different inodes, right? One could do that potentially, and one of the solutions we're going to look at is similar in spirit, but that's not a very performant design in the general case. See, basically whenever you're doing systems design, you basically want to say, I want to speed up, I want to make my general case as fast as possible and yet cover for the rare cases, right? It's a bad design to actually slow down your general case to take care of rare case, and if you're doing that, then that's a that's basically an example of that. All right. So recall that a random read takes 10 milliseconds, right? And so basically that means that if I was to do FS check, then the time it will probably take me to do a full FS check would be somewhere like number of inodes, which is representing of number of files in the system, and let's say each inode is taking one random read, so you're going to take n inodes by 100 seconds, right? So you can do 100 inode reads per second, so depending on the number of files you will do n inodes upon 100 seconds, and that's really slow, right? If you have thousands of files, that's easily an hour right there. As a data point, FS check takes around 10 minutes per 70 GB disk with 2 million inodes. Right. So clearly, in doing so, it's instead of doing a random read per inode, the better thing to do would be, if you're actually doing a full file system scan, the better thing to do would be do a sequential read to read up all the inodes into memory and then do your traversal, right? But even if you're doing that, so this is the optimized statistic. So even if you're doing that, a disk which is roughly 100 GBs takes tens of minutes, right? A disk that's terabytes will take hours, and so on. And so as the disks started to become larger and larger, this idea of doing an FS check on a reboot started becoming less and less practical. All right. Okay. So I'm going to discuss another method to be able to do this cache recovery. But before that, let's also discuss. So we have discussed one method, which is ordering, and with synchronous writes. By synchronous writes, I mean write through cache, right? So whenever I write straight to disk. There's no write back going on. The other thing about synchronous write is it's very slow, right? So let's say I just imagine that you were to untar a tar file. So and let's say the tar file has 1,000 files inside it. So just untarring a tar file requires creation of 1,000 inodes, and creation of each inode, if it's a sync write, is going to take 10 milliseconds. So 1,000 inodes will take 10 seconds to untar one small tar file which has 1,000 files only, right? So sync writes is not very practical. On the other hand, if you had a write back cache, it would have done this whole untar operation in almost 0 milliseconds, or less than a millisecond basically. So you want write back, and so the way this is done, if you wanted to implement ordering with write back cache, you would make the updates in the cache, but also store in the cache in memory the ordering dependencies between disk blocks, right? So let's say I wanted to do a create. I'll first write to child inode, initialize it, and then write to parent inode, right? Parent directory inode, let's say. And so let's say these are the two things I have to do. There are a few other things that's to be done, but let's say there's these two things to be done. You have to write to the child inode, and then you have to write to the parent inode. So what you will do is you will do these writes in the cache, but you will attach some ordering number to these. So for example, you will say that this should be done. There's an ordering dependency between the second block and the first block. So the second block should be flushed only after the first block is flushed to disk. So at the time of actually doing the replacement or flushing or writing it back in a bunch, you're going to make sure that the things are ordered. Okay. So for example, you have multiple disk blocks. Let's say this is A's disk block and this is B's disk block, and let's say A and B are directories. Then if I say move foo A/foo to B/foo, and I want to make sure that creation happens before unlink, then I'll say that I'll draw an edge from B to A, saying that B should be flushed before A is flushed, creation should happen before unlink. Right? On the other hand, let's say after that somebody executed a command called mv b/bar to a/bar. So somebody executed yet another command, and so this time you wanted to draw an edge like this. Right? This time you are moving in the opposite direction, so you basically want to first create a link in bar, and then remove the link from in A, and then remove the link from B. Right? This time you basically want to say that this should happen before this. Right? And here's an example where this dependency graph could have a cycle. And if it has a cycle, then at the time of flushing it back to disk, it's unclear which one you should flush first. Right? Let's say you flushed A first, then you have lost. It's possible that if there's a crash that happens after you flushed A, then you may have lost the link to foo. Right? So foo's contents may have been lost. On the other hand, if you flush B first, then bar's contents could have been lost. Okay? So here's a cycle. So how do you resolve something like this?
Take the ordering what is to be updated in A and what is to be updated in B, as in not just the whole update of A and then the whole update.
Okay, so here's a suggestion. I'm maintaining ordering at block granularity. I'm saying this block should be committed to disk or written to disk before that block. I'm without going into semantics of what is inside the contents of the block. And so suggestion is, instead of saying that this block should be committed before that block, say these contents in this block should be committed before those contents in that block. That's not a practical solution, right? Because there's too much semantic information that needs to be stored, and it's basically almost like writing. At flushing time, you have to basically look at the semantics of what's written, at what bytes that has been written, it's a directory or etc. I mean, these are the kind of things you don't want to worry about at flushing time. All you want to care about is, here are some disk blocks that are in the cache, they are dirty, they need to be written back to disk. What's the other thing you can do? Well, here's one suggestion. When this operation gets executed, in memory the OS figures out that, hey, there's going to be a cycle in your dependency graph. So when you see that there's a possibility of a cycle, you stop that operation and you flush these disk blocks to disk, such that this edge gets removed. So once you flush them to disk, the old edges will get removed, which means the old state will get consistent, and now you can perform this new thing. Right? So every time you're making an operation, you check the dependency graph. If you see a cycle, you hold on, you flush the blocks that are involved to the disk, so that the old edges get removed, and so the new edges can get created without having a cycle in your dependency graph. Okay. So ordering with write back and coupled with an fscheck program has been a popular solution for a long time, but with growing disk sizes, it has become relatively unpopular. And the other way to do cache recovery is logging. So let's see how logging works. So the idea is that, let's say there's some system call, let's say there's create, and it's going to do write to block 10, then 100, and so on, right? And that's it. And you want to make sure that these operations are atomic with respect to power failures. So there's some operation that's going to have multiple disk writes, and you want to have them atomic with respect to power failures. Here's one way you could do it. Each time you see something like this, you basically don't write the disk blocks to the file system at this point. You keep recording these operations in a log. So basically start logging. You maintain a separate data structure called a log on disk, and each time you want to write something, you basically log this operation. So you say that I want to write to block 10 with these contents, and you put that in the log. When you put it in the log, you're basically indicating your intention that you want to write to this disk block, you are not actually written it to the disk block, right. So you log each operation, log each write I should say to log, right, to disk. Okay. After you're done logging each of these writes, you append a commit record to log on disk, right. So you basically first write that I want to write to all these blocks, and then you append a commit record to the log on disk, all right, and your operation is complete only after the commit record has been written. If there is a power failure before the commit record has been written, it is as though none of these writes have happened. If there is a power failure after the commit record has been written, it is as though all these writes have happened. Okay. So let us see, I have a disk, let us say I was to draw the disk data structure. So I have some tree like structures, different types of trees, one is a directory tree and other is an inode tree and so on. So there are tree like structures on the disk. So this is, let me call this the file system, and then there is a sequential structure which I call the log. Each time I want to make an operation, I basically start writing to the log, and then I write a commit. Recall that we made the assumption that the write of a sector is atomic to the disk. So either the entire commit will be written or none of the commit will be written. It's not like half of the record can get written. So this operation is atomic, and you're using this operation to basically make the entire operation, the entire sequence of writes atomic. And after you've written the commit block, you are going to asynchronously make these writes to the file system. All right, that's after you've written the commit record. So let's see once again. I wanted to make an atomic operation which involved multiple disk writes. I will create a new transaction. So this entire thing can be called a transaction. So I'll create a new transaction. I will log the blocks that I need to write and log them to the log, and then I'll write a commit record to the log. After that, I'm done. As far as I'm concerned, the disk is in a consistent state, and asynchronously I'm going to copy the blocks in the log to their respective positions on the file system. Right? Recall that all these logs have annotation saying block 10 contains X, block 100 contains Y, and so on. And so asynchronously I'm going to write these blocks from log to the file system. Now let's see what happens if there's a crash. If there's a crash before the commit record was written, no problem, it's as though nothing happened, right. If there's a crash after the commit record has been written, but before you have started applying the changes to the disk, no problem, the operation has finished atomically, and now you can do the same thing. So at recovery you can just apply the log to the file system. What happens if the crash happens in the middle of application of this log to the file system? So let's say I've written the commit record. After that, I was asynchronously writing block 10, and before I could write block 100, there's a power failure. No problem. At recovery time, you will again write 10, but with the same contents, so there's no problem. Right? You will just overwrite the 10 again, but with the same contents. That's no problem either. Right? So this is nothing but a write ahead log. Okay, where whatever you want to write, you write it to the log first, and you keep doing this, and then you write a commit record. After that, you actually push all those writes asynchronously to the real file system. So we are all convinced that this will ensure consistent state even across random crashes in terms of power failures. notice that the write of the commit record on the log is acting as a serialization point. If a power failure happens before the commit record, it's as though the transaction didn't happen at all. If the crash happens after the writing the commit record, it's as though the transaction happened in completion. Even if there's a crash that's happening in the middle of your application of the log to the file system, it's still consistent. Right? This data structure of the file system plus log will always remain in a consistent state. There's no inconsistency that can happen. Okay, all right. So how does one write code to do this? Let's say I have a syscall like create. I'll just say begin transaction, then write, read, etc. and then I'll say commit transaction. Okay. So all I have done is that all the operations that I wanted to make atomic with respect to power failures, I have bracketed them with begin and commit transaction calls, right? Just like very similar to your locking, acquire and release. Right? And so begin transaction is going to write to the log that I'm starting a transaction. All these operations are going to append records to the log, and then commit transaction is going to write the commit record on the log. And there's going to be an other thread that's asynchronously going to apply the log to your file system. Right. So it's very easy to write. To basically, the code structure doesn't change much. You just have to enclose things that you want to make atomic with begin transaction and append transaction. After you are done applying the log, applying the transaction to the file system, you can delete the log. You can delete the transaction from the log so that it can get reused. Right? So till it has not been applied to the file system, you have to keep it around. But after you have applied it to the file system, you can now free it for use for the next operation. Right. Okay. So what's wrong? Or what don't we like about this performance, right? What are some things that are happening? Firstly, everything that I need to write twice. I need to write first to the log and then to the file system. So every operation basically has a 2x overhead in some sense, right? So 2x writes. Okay. The second thing is I log whole blocks even if few bytes written. So even if I just update 1 byte in the block, I log the entire block in my log. So my log space overhead is larger than what you would have wanted it to be. Eager write to log. I'm very eager to write to the log. Every time I do a write, I basically immediately want to write to the log, right? And as soon as I do a commit, I want to basically make sure that the commit record has been written to the log. And then later I'm going to write it to the file system. Okay. So is this avoidable? Can we not have eager write to logs to the log? Well, we'll see this in the next lecture. But as it stands now, this thing has a very bad performance. Each time I want to make a write, I actually need to go to the log and make this write. One simple optimization could be you don't do the writes to the log as they are being done. You wait for the commit transaction to happen, and then all these 4 or 5 records that you've written can be written in one batch to the transaction, to the log. Right? This is a small optimization, but this is still not good enough. Okay, why is this not good enough? I still need to do this eager write on every commit. So there's not write back in the true sense. Every operation needs to be synchronously committed, every atomic operation. I would have wanted that even atomic operations can be written back using a write back cache. Right? I want my write back cache to have more freedom in or more batching than just 4 or 5 disk operations. Okay. All right. Then write to file system. So write to file system, as we discussed, can be done lazily. So this is okay, right? Here we are saying that once you return it to the log, you basically lazily apply the log to the file system, and you can batch it and thus get a lot of performance. Right? Okay, there's a question.
Sir, suppose if we update the log after every 4-5 operations and whenever there is a commit. So, but in that case, before that we are just writing to a cache. Now, but suppose if there is a power failure while I am writing to the log from the cache, and the commit keyword is written, but other operations are not.
Okay. Okay. So good question. I'm saying, there's an optimization that a transaction need not be written to disk, or the blocks in a transaction need not be written to disk eagerly. You can keep them in cache, and then at commit time write the entire log transaction to the log in one go. And the question is, when you're writing it back, if the commit happens before, if the commit is written before the other blocks, then there's a problem, right? So at the time of flushing it, you have to basically make sure that there's some ordering in which you are doing it. Typically, the way this will be done is that you will issue all the transaction records in one go. So all the transaction records happen in one go, and then the commit record happens in a second iteration. So in that way, you have two sequential writes to the disk, right? So you waste one full rotation. Assuming that the log is written sequentially, you first make one sequential write to write the entire transactions blocks, and then you make one sequential write to write the commit. And just to make the ordering, you have to do 2 instead of 1, so that the disk doesn't reorder them internally. Modern disk interfaces allow you to specify that here are 5 writes, but make sure that this 6th write is after this all these 5. So that way you can even avoid this extra overhead of multiple writes. Okay, good. Okay, so we've seen logging in its very raw form, where we are using the log. We are eagerly writing to the log. We are logging the whole blocks, and eagerly in the sense at commit time. Also, we are making another problem with this thing is that only one transaction at a time. Right? Why is this true? Let's see. Let's say I have this code, begin transaction, and then I start writing something, and then I commit transaction. To ensure atomicity across between multiple accesses to the file system, the way I have discussed it so far, you basically want to make sure that only one transaction is active at any time. If the multiple transactions active at any time, then there are more problems to be dealt with. Right? So the way we have discussed it so far, there's only one transaction that can be active at any time, and that in itself is a very big performance problem, because if there are lots of users running lots of programs to completely different parts of the file system, they get serialized because of this common log across the entire file system. Right? So not a good idea at all. All right. So let's see how we can fix it. And I'm going to look at the ext3 file system on Linux. Right. So the ext2 file system was basically based on the ordering and fscheck program that we discussed earlier, but the ext3 file system introduced logging, and but in an efficient way, and we're going to see exactly how this is done. So we saw some problems with the way that we have discussed so far, and let's look at what can be done. Firstly, a transaction is not one operation but multiple operations. So if there are 100 creates happening at the same time, they are all made part of one transaction. Okay. So a transaction basically represents some kind of locality in time. So you basically say I start a transaction and all the file writes that are happening now will belong to this transaction, and then at some point I'm going to say stop transaction. When I say stop transaction, all the operations that are completed belong to this transaction, and all the operations that are ongoing I'll wait for them to complete, and when they complete, all these operations together form one atomic unit, right? And this atomic unit gets flushed to disk in a log, and then there's one commit record for this entire big chunk of writes, possibly by multiple users, multiple processes, different parts of the file system, completely different operations, right? So what you're doing is you're making you're clubbing lots of different atomic operations into one large transaction. Okay. So basically what this means is that these begin transactions and commit transactions can be replaced by begin operation and commit operation, and it's not necessary that at the time of committing the operation you actually commit the transaction on disk. You just basically say that the operation is finished, and so the invariant is that a transaction will have either the entire operation in it or none of the operation in it, and a transaction will never have half of an operation. Okay. And so you basically club lots of different operations into one transaction, and so that gets rid of some problems. So for example, only one transaction at a time, you have solved it, right? So you can have lots of different operations at the same time, and then you can choose to commit them at your own will. How do you choose when to commit a transaction? You can say every 5 seconds, every 30 seconds, completely reasonable choice, right? So for example, modern operating systems don't give you any guarantee about if you're writing something whether it's actually persistent on disk or not, but every 30 seconds, let's say, the transaction will get closed, and so because the transaction got closed, it will get written onto the disk, and at that point you can be sure that the data, whatever you wrote 30 seconds ago is very likely on the disk now, right? So this interval, so you can just choose to close the transaction at will whenever you like, and when you close the transaction, at that point you make sure that all the operations that started before the close of the transaction will get committed on disk, right? So you fixed this. You also fixed eager write to log. So now you can, because you are using a transaction worth of 30 seconds of writes, you can actually batch all of them and write them all together, and so it's not an eager write of log to log. You actually, instead of writing 6 operations, you're writing 6,000 operations together to the disk. So that's much more efficient. Right. So this one is already good. Write to FS is lazy. Log whole blocks even if few bytes are written. So they still log whole blocks even if few bytes are written, because it's very hard to keep track of which bytes have been written and which not. So you log the whole blocks. But the nice thing is, because you are making the transaction so big, if there are multiple operations that wrote to the same block, so you log the whole blocks even in ext3. But the nice thing is, because you're doing lots of different operations batching into one transaction, you don't have to, these blocks may have been modified many times within the same transaction, and you don't need to record all those blocks, all those different versions of the blocks. You only need to log the final version of the block. So let's say if this block was modified 1,000 times in this 30-second interval, all you need to log to disk is the last value. So you still log the whole block, but you just absorb lots of writes in doing so. So this also becomes better. All right, and 2x writes remains, but the nice thing is, because you are batching so many writes together in log, right? It's a complete sequential write to the log, so that's very fast. As we know, there's only one seek and one rotation, and you do a write at 50 to 100 megabytes per second to the log, so that's very fast. Also, now all these writes now need to be applied to file system, but that's a huge transaction. So because it's a large transaction, you can have lots of IOs in flight simultaneously, so writing to the disk is also faster. You have much better disk bandwidth utilization. So essentially, the larger the transactions, the less the 2x write problem is, right? And because I have made my transactions as large as I want, there's no problem, right? So let's look at how ext3 works. So let's look at an ext3 transaction. Open one transaction at a time. On start op, add the op to ongoing transaction. Right. This is all in-memory operations. Each time somebody starts an op, you basically add the op to the ongoing transaction, and commit transaction every few seconds, or every few tens of seconds, depending on what you want, how much reliability and performance trade-off you want. Okay. Let's see how do you commit a transaction. Okay. Firstly, open a new transaction. So when you are committing a transaction, you basically say that all new ops will now belong to the next transaction. So you basically first close your current transaction, which basically means any operations that are happening after this point will now belong to the next transaction. Okay. Mark this transaction as done. Wait for in progress ops to finish. So there could be some ops that have started but have not yet committed or haven't stopped, finished. Right? When you close the transaction, there are some partially completed ops. So you just want to wait for those ops to finish before you actually write the commit record. Right? So that's how you're basically maintaining atomicity, right? You have basically said that I can close the transaction at any point you want, but when you close it, you also wait for all ongoing or all operations that have started before this close to finish. So that's how you basically ensure atomicity of each operation. Okay. Then write descriptors. So descriptors are basically these blocks which contain meta information about which block and etc., which block, which version number, etc., and then what's the data, right? Descriptors and blocks to log and wait, right, and then write the commit record. And that's it, right? That's your finish. That's your commit transaction. And then asynchronously, you are going to write the contents or whatever the log is saying to the file system. Okay. Allow So after you've written the commit block, you can now allow the blocks that have whose contents have been logged in the block transaction to now get written to the actual file system. All right, let's stop here and let's discuss the ext3 file system in more detail next time.